All right, hello again, Algebra 2. This is section 2.6, which is about special functions. Basically, in this section, we're going to be graphing some different kind of functions, not just lines. We're going to be graphing piecewise functions, and we're going to be graphing step functions and absolute value functions. So we're going to learn what those all look like and how to graph them. We have this vocabulary that you'll be looking for in this section. Again, we're mostly going to be defining it as we go through, but by the end you should know what each of these words or phrases means. We're going to start with piecewise function. A piecewise defined function, like it says here, is a function that is written using two or more expressions. It's called a piecewise defined function. So if we look up here, this is a federal tax rate schedule. This is not a linear function because each piece is defined by a different expression. So here there's 15%, 10%, 25%, 28%. So it's not the same all the way along. Each interval, if we could say that, would need a different kind of expression to define that piece of the graph. That's why these are called piecewise defined functions. Just like when we do inequalities, if I'm graphing a piecewise defined function, if I have a solid dot, it means that that point is included on the graph. And if I have an open dot, it means that point is not included, which you'll see in the next example. All right, so we're going to graph this piecewise defined function. Let's look at what it is first. So f of x, this tells me it's a function, equals. There are two different pieces, x minus 1 and negative 1. So basically I have two equations, y equals x minus 1, or f of x equals x minus 1, and y equals 1. If x is less than or equal to 3, my graph looks like the line x minus 1, which is a line with a slope of positive 1 and a y-intercept of negative 1. If x is greater than 3, my function looks like y equals negative 1, which is just a horizontal line. Okay, so what we're going to do is we're going to start by graphing this first piece. We're going to start at 3, right? So at the point 3, x minus 1, if I plug in 3, 3 minus 1 is 2. So the point 3, 2 is on my graph, and it's a closed circle because of this equal to symbol. Now, this is only defined for values less than or equal to 3. So to the right of 3 over here, this function does not exist. It only exists to the left. So basically, we graph a line. This line has a slope of positive 1, so I go down 1 and to the left 1, down 1 and to the left 1, and so on, and I draw that line. So this line does not go forever in two directions. It only goes forever in one direction. It's like a ray from geometry. Then, to graph my second piece, I'm going to graph an open circle at 3, negative 1. Why am I starting at 3, negative 1? Because negative 1, remember that is a horizontal line, y equals negative 1, and it's going to be this horizontal line here, but it's only defined for x is greater than 3. Since there's no equal sign under that, that's why I start with an open circle, and I only draw my line to the right. So in total, my piecewise function would look like this. It has one piece that looks like x minus 1 that goes to the left of 3, and one piece that looks like y equals negative 1 going to the right. I have a closed circle here and an open circle here. The values that are y coordinates are all real numbers less than or equal to 2. That means there are no y values up here anywhere on my graph, right? This is where my graph starts, and then I cover all y values below that. So the range is the set of f of x, or the set of y, such that f of x is less than or equal to 2. All right, pause and answer this question for me. All right, the answer to this one is C. The domain is all real numbers. There's no x value I can find that would not be able to be plugged into this graph. I can plug in all x's less than or equal to negative 1 and greater than negative 1. 2x plus 1 is this line here. And negative 3, y equals negative 3, is this ray here, I should say ray. And my range is y is greater than negative 1, that's for this part. Here, y is negative 1, and that line goes forever above it. Or y equals negative 3. So there's no y values below -3. There's no y values between -1 and -3. So my range is just y is greater than -1 or y is equal to -3. All right, what we're going to do here is go from a graph and write our piecewise function. So if we analyze this a little bit, this is a horizontal line, so I know it's going to be y equals, and it's 1 unit above the x-axis, so I know that's y equals 1. If I look at this line here, it has a y-intercept of -4, and it looks like it has a slope of 1. If I count from this point, I would go up 1 to the right 1, up 1 to the right 1. So with a slope of 1 and a y-intercept of -4, this would be my equation. Then the next thing we have to look at is the domain values that go with that. So this linear function of y equals x minus 4 is only defined for x is less than 2. So it starts at 2, but notice the circle is open, so its x is less than 2. I shouldn't draw lines under that or else it looks like equal to. X is less than 2. The right portion of this graph has a filled in dot at 2, at x equals 2, and so that's going to be defined for x is greater than or equal to 2. And so our final function would look like this. It's x minus 4 for x is less than -2, and it's 1 if x is greater than or equal to 2. All right, try this one. All right, hopefully you said D. This is 2x plus 10, that's this line here. That one's a little harder to see the equation of because you can't see where it crosses the x-axis. But basically what you would do is you would pick 2 points on the line and find the slope between them. And then you would be able to use point slope form to write the equation of that line. And that's only true for x is less than -4. And then here I have a horizontal line at y equals 7 if x is greater than or equal to -4. All right, this next one is called a step function. Step functions look like steps. So if you look at this graph here, I have a bunch of little line segments that are not connected, but they look like steps. This book calls them a piecewise linear function instead of a piecewise defined function. Basically what they mean by that is that our equation only has one expression, but it still graphs as different pieces. Okay, and one way to do that is with something called the greatest integer function, which we write like this, f of x equals x, but it's inside these kind of double square brackets. And that means the greatest integer less than or equal to x. So for example, if I take the greatest integer function of 3.25, I pick the integer that's directly below 3.25. So if I thought of this on a number line, right, if this is 3 and this is 4, 3.25 would be like right here. The greatest integer function says find the integer that's directly less than or equal to this number. So the integer that is the biggest one that's less than 3.25 is 3. When I talk about -4.6, if again I'm thinking about a number line, -4, -5, -4.6 would be about right here. So the greatest integer that is less than or equal to that is the integer directly to the left on the number line, which is -5. So if we look at this graph, it looks a little bit interesting, right? It looks different than ones we've seen. What's actually happening is that I'm saying, okay, any number from 0 all the way up to, but not including 1, if I plug that in, so if I plug in 0.1, 0.2, 0.3, the integer that will be lower than that is 0. Right? If I plug in my x values of 1, 1.1, 1.2, 1.3, 1.4, the y value that I will get out is 1. Right? That's why it graphs at 1. If I plug in my x values from 2, 2.1, 2.2, 2.3, 2.4, the greatest integer less than or equal to those is 2. So I'm getting ordered pairs from what I plug in, which are my x's, and then what I get out is always going to be an integer. oops, let me erase this. This is just a tip to remember. When I graph the greatest integer function, the domain is all real numbers. I'm allowed to plug in any kind of x I want here, but what I get out is always going to be integers. So the range of this function is all integers. All right, let's take a look at this example. This says, one psychologist charges for counseling sessions at the rate of $85 per hour or any fraction thereof. That means that you're going to get charged $85 per hour, and even if you're only there half an hour, you're still going to get charged $85. We want to draw a graph to represent this situation. This is a real-life step function. So we know that the total charge is going to be a multiple of 85. She doesn't charge partially, right? So if you're there for an hour, you get charged $85. If you're there for an hour and a half, you would get charged 2 times $85 because you would have been there 1 hour plus a fraction of another hour. If the session is more than 0 hours or less than or equal to 1 hour, so if you're there for 15 minutes, 20 minutes, 50 minutes, 1 hour, the cost is $85. Once you go over that hour, she starts charging you the second hour. So if you're there an hour and 15 minutes, an hour and 20 minutes, an hour and a half, you would get charged $170, and it would continue like that. So what happens is we basically make a table of values where our x is a range. So I'm saying any x value between 0 and 1, including 1, you get charged $85. Once I go over 1, I start getting charged $170 all the way up until I hit 2 hours. If I'm there for 2 hours and 1 minute, she's going to start charging me an extra $85. So that would be $255 in total. What that looks like on a graph is like this. Notice we labeled our y-axis with multiples of 85. And so it's an open circle here. All the way until I hit 1 hour, I would get charged $85. As soon as I pass 1 hour, I jump up to $170, and so on. All right, let's look at this one. Oops, I guess I have the graph showing up there. This is h of x equals the greatest integer function of the quantity x minus 5. Okay, here I have the basically table of values that would go with this graph. So, oh, I'm sorry, I made a little mistake. Let me fix that. So we will practice more with these tomorrow, but let's just look at what's happening. If I plug the number -2 into my greatest integer function, I get the greatest integer greater than, less than, or equal to -2 minus 5. Right, so I end up with this. Well, the greatest integer that's less than or equal to -7 is -7. If I plug in -2.1, then I would end up with -6.9 inside of here, and my greatest integer that's less than or equal to that would still be -7. So anywhere from -2 to -1, including -2, let's see if you can kind of see it there, it's this part right here, would be down at -7. And that works the same for each range of values all the way along the graph. Again, we'll practice this more in class tomorrow, but the key is that you recognize that this function is the greatest integer less than or equal to whatever's on the inside. So again, this domain is going to be all real numbers, and the range is only going to be integers. All you can get out for the y are integer values. Okay, here's one for you to try on your own. See if you can match which graph would go with this situation. All right, you should have answered A. My range is going to be multiples of $1.25. All right, let's talk absolute value. This is something you've graphed before. Absolute values always graph as pointy V's, and we can define absolute value actually as a piecewise function. It's x, which is this line over here, if x is greater than 0. It's 0 if x equals 0. And it's negative x if x is less than 0. So it's always V-shaped, its domain is all real numbers, and if it's like this without anything added or subtracted, because this is the parent function, meaning the most basic one, then its range is all non-negative numbers. All right, we're running out of a little bit of time on this video, but if you look at this example, basically what you do for absolute value is you make a table of values, and then you graph them. So if we were to graph the absolute value of x plus 1, this is what we would get. Notice that instead of being at 0, 0, it's moved up 1 unit to have its vertex at 0, 1, and that's because of this plus 1 that's right here. And we will finish this tomorrow.